me restart this and that out. Might need to go back. We need to stop sharing and do it again. Okay, there we go. All right, that's better. Thank you. Okay, so we did spec some of the shortcomings of spec in terms of cardiovascular imaging technique were the spatial resolution was pretty poor. I mean, there were sort of blurograms and blobograms, they had big convolution there. And also we got images whose brightness of activity was good for evaluating relative amounts of flow in the heart, but not absolute flow. And part of the reason for that was it took a while to acquire the data. And so getting the dynamics of how flow goes into the myocardium was difficult. PET offers an alternative to SPECT. It still uses a radionucleide. It uses radioactivity inside the patient to achieve a signal. And the nice thing about PET is the data can be acquired more rapidly, and the spatial resolution, as we'll see from the technique itself, is higher because you essentially have, as we'll see, a very thin line of sight or line of activity from which your signal could emerge when you detect it. And we'll see. So it's a really interesting technology. You can use it to actually do some fundamental biochemical measurements or biochemistry of the cells that you're imaging, as opposed to just looking at blood flow and things like that. The structure or what a scanner looks like is similar to the other scanners we've seen thus far. So it's a cylinder. The patient table's here. The patient can be moved in and out to different positions inside the cylinder. At the front end of this cylinder, virtually on every PET scanner that's sold now, there will be a CT scanner mounted to the end, so that the first thing you do with the patient is acquire a CT, much like we saw with SPECT. And this is to, again, compute what the attenuation correction should be. So given a pathway out of a patient, how much tissue does the photon have to get through to get to the detector? And that will vary a lot depending on which pathway we're looking at. And so we want to include that in the reconstruction. So that map is constructed using CT data, right? What else? The really interesting thing about PET is the agent that we put in can also be biochemically active. And so you can create an atom and then put it on a biochemical molecule and stick that molecule in a patient. And that molecule can get taken up like it's a sugar or like it's an ion through a sodium-potassium channel or something like that. And it will give you a picture of where the stuff went and a picture of how did the tissue respond to the stuff when it got there? Like, did it take it up or just spit it out? I would say the vast majority of PET scans done in the hospital or in a major teaching center hospital will be cancer patients. And the reason for that is cancer cells themselves have a high metabolic activity, usually higher than the surrounding tissue. And if you put an agent in that is sensitive to that metabolism, it gets taken up by cells that are in a high metabolic state, then you can see very small tumors. And normally this is what you would do if you had say you had a primary tumor in your brain. And you have it surgically debulked, you have radiation therapy and chemotherapy. 6 weeks, 2 months after all of that, you go back in and you get a PET scan of your entire body. And it's to see whether or not there are remaining metastases of that tumor around your body. The cool thing about PET is you can detect very small objects. You might not image the perfect shape of that ball of cells, but because of the brightness, you'll know they're there, right? And you can pick up a very small number of them because of the sensitivity of this technique. So this is how it works. You have a radionuclide, it's called, and in its nuclear decay, which will happen over a minute's time frame, so you have some agent that you've created, and we'll see how you create it. It will emit positrons as part of the nuclear decay of the atom. And so if we're starting with this F18 molecule, which has a 110-minute half-life to be converted to oxygen 18 through a nuclear decay, this is just one pathway it could take. During that decay, a positively charged electron is emitted. So the antiparticle for an electron is emitted, and it's called a positron. It has its own name. Most particles have an antiparticle that is the charge is flipped, and but they're just called an anti-neutrino or something. They don't have their own name, but this one does. The anti-electron is called a positron. It's exactly the same as an electron. Its mass and everything else is exactly the same. It has a spin. However, if it sees an electron and they collide, they interact with each other and annihilate each other. And so you have this conservation of charge and everything because they've annihilated each other. And what comes out of that annihilation is two photons. And those two photons go in exactly opposite directions to within a couple of degrees, right? And each one of the photons is a half an MeV, so 500 keV. Remember, in SPECT, we're looking at 140 keV photons. And in X-ray imaging, we look anywhere between, say, 40 keV to 140 keV. Those are the photons we're looking at. These ones have much higher energy. They're up at 511 keV, or half an MeV. And they fly away at the speed of light out of the patient in opposite directions, right? And so the thing you have to keep in mind when evaluating spatial resolution of PET also is that the positron will wander in a random path through the patient before it interacts with an electron. And that wandering depends on the energy with which the positron is ejected from the nucleus. So it depends on the agent. But it's on the order of millimeters. We'll have a little chart. We'll say, how far on average does the positron get before it annihilates. So here's the essence of the high spatial resolution for this technique. Just like in SPECT, we're going to have detectors and a detector array around the patient. And this 500 keV photon will interact with a crystal in the detector and cause a flash, okay? And the detector material is special such that it's tuned to interact with high energy photons up at 511 keV. And recall, we have a positron emitted here, hits an electron, two photons come out simultaneously. So what we can do is we can look for coincident flashes because they're going to hit the detector at the same time. The speed of light from here to here, we're talking like under a nanosecond or something, around a nanosecond. So it's a very short path length. So unless you have a super high frequency detector working up in megahertz or something, you're going to see this as a as essentially a coincident event, a flash here and a flash here. So we use the computer on board the PET scanner to determine when do we get these synchronous coincident flashes. And if we see one, we record it and we record the position at which the flashes occurred. And we know that the agent is somewhere along the line between those two flashes. We don't know what depth along that line, but we do know it's along that line, right? Which is a very strong piece of information because we haven't used any kind of anti-scatter grid with SEPTA or anything to do this. We've just used this coincident detection. So we can build these detectors such that they work really fast, and we don't have to put a grid over the top to get the resolution in the theta direction, right? So as you can imagine, if we get thousands of these per second, we can build up a very large list of these lines, right? So you just have to have the two detectors on either side and just list them out as this all happens, right? And then, so we just keep making that list. The rate at which the list updates is going to decrease over time as the agent decreases its emission over time because it has a half-life. Eventually, it's just going to stop emitting, right? A long time down. So this agent has a long half-life. This fluorine 18 is 110 minutes. So it's like 2 hours. It's still going at half the rate, right? That makes it very convenient to use, obviously. We'll see some agents have like half-lives of, 48 seconds or something. So you have to image really quickly, right, to get that done. In the slice direction, so here's the patient's head would be here, their feet down here, and this is the table going through the scanner. You can put these septa in that direction if you want to collect a single slice, right? So you eliminate basically events in these highly angled pathways. However, you don't have to do that. You can just keep track of everything in 3D, right? And so it'll make the reconstruction a little harder, right? Because now we're going to have like a set of 3D kind of projections as opposed to just 2D projections in an XY plane. But most of the scanners now will do this 3D and will do an iterative reconstruction process by which you use all of the 3D information to reconstruct a 3D image. And as you can imagine, everything is going to move to reconstruction just run by deep learning, right? So we can do thousands of them to train. So this is called the line of response, right? And in the ideal world, we're looking down the bore of the scanner, and here's a cross-section of the patient, and an event occurs. The photons come out, we get a flash here and a flash here. And so we have this line, and we stick it in our database of lines. Same things can go wrong here as went wrong with SPECT, remember? So if I have an event here, and the 511 keV photon comes this way, another 511 keV photon comes this way and interacts with the tissue. It can hit a nucleus, it can hit an electron, it can interact in whatever way photons interact with things. It can get totally absorbed, but it can also have a highly elastic collision where you dump energy in here as something comes off, like an electron or something like that, and then the photon goes in a different direction. This has probably a fairly low probability of a scattering at this high angle, but it's finite, right? There is a probability that's going to happen. And now you get a flash here and a flash here. And so the time for that is about the same. And so this looks like our line of response would be this. And so that gets chalked up to scatter, right? You can also have a miracle can occur and two, electrons and positron pairs annihilate at precisely the same time at two places in the sample. right? And then you would get, if nothing happened in terms of scatter, you would get a flash here, a flash here, a flash here, and a flash here. So now you don't really know which one is the line of response. And so once again, it gets bundled into a background signal, which is called scatter. Okay. Again, you can use energy discrimination to throw this one out because this photon is going to have less energy than the 511 keV. And so if you put some kind of energy filter on here, the height of the peak, you can filter some of those out. This is what a modern crystal looks like for essentially detecting the 511 keV photon. Remember those photomultiplier tubes? The way these things are set up, you have 4 photomultiplier tubes attached to a crystal that is created with these lines of activity so that the flash doesn't spread out in the whole crystal. It tries to go down one channel. So this would be light reflecting edges down these slits. The crystals can be made of different materials. And this is a typical window time for this BGO is 12 nanoseconds. So that means you can make separate detections every 12 nanoseconds, right? Why not faster than that? Remember, it's like 1 nanosecond for the photon to get out. The problem with the optical detection is that the flash itself has a decay. So you get a peak of light, and then the light decays away over time. And so that thing has a width, that signal. And so there's some uncertainty as to when in that width that signal occurred. And so in exactly the same way as before, if I have a flash here, right, I know that my signal, the detection at this PMT is going to be much higher than this one and this one and this one. And so I can position my estimate of my flash with higher resolution than the detectors themselves. So remember in the SPECT camera situation, we had a detector we rotated around the sample, and we were collecting lines of response for SPECT in basically a set of parallel directions for each orientation of the detector. So not very efficient, right? So we're only detecting basically one projection per time, per angle that we set this thing. And it just sit there and we get that angle and then click it and get another angle. So all of the photons flying out in every other direction are being lost, right? Whereas in PET, we don't rotate a detector. We just have a fixed detector. It's sitting in that position. And because here we had to have septa that were parallel to this detector. Here, we can have septa in the Z direction, but you can also just have 3D such that these things are continuously collecting data. So you get a lot more data per unit time because everything's open and reading the data at the same time, right? So that means that we can collect a critical number of events and lines, of response per unit time and build up our projections much more quickly. Oh, this just shows again the source of scatter, essentially. So modern PET system, if you're going to estimate its full width at half max, a round number is 5 millimeters full width at half max. And so that means if we took a little 1 millimeter diameter liquid ball, like a little vitamin tablet, and injected it with this fluoroxyglucose 18 or some other agent and put it in the scanner, so now it's a small little signal. What will come out is a 3-dimensional Gaussian ball of signal with a full width at half max of about 5 millimeters. Okay. That seems like a lot, like seems pretty broad, right? Given the fact that we would like to image things like a coronary vessel that has a full diameter of 4 millimeters. So this is kind of a blurry picture to do that kind of thing. So as long as you're imaging something that it's not necessary to get high definition, high detail on edges, but if you want to see if something's in there and it's actually cooking, you just a positive signal sometimes is enough. So you can imagine if I wanted to do metabolic imaging of a coronary artery to find out, is it inflamed? Is there a response to some kind of hyperemia, something like that? If you're doing inflammation imaging, you basically just need a positive signal anywhere in the coronary. It doesn't have to be detailed down to which part of the coronary wall or something. Just a positive signal there will tell you, yeah, there's something going on in there. There's inflammation. These cells are hot, right? So you're not going to image it, but you're going to understand what's going on biochemically in there. So the factors that cause the spatial resolution to be 5, so the intrinsic spatial resolution of those detectors, right? The distance traveled by the positrons before annihilation, which is something you really can't get rid of unless you focus your attention on positrons that have low energy when they come out, right? So they're not going to scatter much around. And there's also the fact that there's a slight angle. It's not a perfect 180 degrees. It's 180 plus or minus 2 degrees, I think, on the angle at which those photons come out from the event. So here's an exaggerated picture of why some of the lines of response will have lower resolution than others. So if I have an event somewhere on this line of response here, the photons will go into detector A and detector B, and they're somewhere inside this width, which is the width of those two detectors, right? If it was over here, I could have an angle coming all the way up here and still hit this one down there. So that's the highest variability of that line of response angle. If my event is off center, then it will come and hit the detector from the side. And so the detector has a wider sort of acceptance window for that photon. And that creates a larger width of uncertainty for where the line of response is. So that's as we move away from the actual center of the detector array. So positron emitting radionuclides. So these are the big ones that are used in both cancer and in cardiology. Rubidium-82 is used a lot in cardiology because it is I forget what it's called when it's called a fake molecule, but it looks to the cell like sodium. So it gets taken up in the sodium potassium pump action of the cell. And so if it is around, it will get sucked into the cell through this mechanism. And that tells you that at least the cell's alive and pumping, right? So metabolically, it's still trying to keep the battery, the resting voltage of the cell at the minus 80 millivolts or whatever it has to be to fire. So that's potentially used to fire off the excitation of the cell. So that gets taken up into that. F18 is usually put on a molecule called fluorodeoxyglucose. And so you take a sugar, and instead of one of the hydroxyl groups, you put this F18 molecule on it. So now it's a modified sugar, and that just gets thrown in and metabolized. Oxygen 15 is used mostly in water. So you would make H2O with the O being this oxygen 15 instead of the normal oxygen. And oxygen is a fantastic perfusion tracer because it goes everywhere quickly, right? There's no blood-brain barrier. There's nothing to stop it. It's just going to flow right through membranes and everything. Okay. Nitrogen 13 and carbon 11. Carbon 11 can be put into any old organic molecule, right? So anything that has a lot of carbons in it, you can load it up with carbon 11s if you know how to do the biochemistry, and then put that into circulation. So a lot of times this carbon 11 is put into acetate, and acetate, it turns out, is a molecule in the Krebs cycle. And I don't know who's memorized the Krebs cycle and remembered it up to this point, but I memorized it twice for exams, and I can't tell you, I've forgotten it already. That was 40 years ago though. So, but anyway, it's in there, right? And just whoop, you inject this radionuclide into that process, and you're into the straight metabolic, turnover of sugars in the cell. Notice they have remarkably different half-lives. Okay, so this rubidium half-life is like 1 minute. So after 5 minutes, that thing is pretty darn low, right? It's 1/2 to the fifth, right? So you got to get this done quickly. However, if what you're measuring is perfusion, you kind of want to get it done in about 30 heartbeats, right? Just like inject and then measure over those heartbeats how the stuff gets taken up and then how it washes up, right? So the fact that it's 1 minute, it's not such a bad thing because it goes away. So most of your you can see a uptake and a washout with that agent. This water agent, also 2 minutes, very rapid. And these are somewhere in the middle, and this is really long. So these are the energy of the positron as it's ejected from the nucleus. And as I said before, it's highly variable. This one's coming out at 3 MeV. It's like firing out pretty fast. And so it's probably going to make a bigger ball of uncertainty as to where the positron gets annihilated with an electron. Whereas this one's coming off with much lower energy, and so it's probably a tighter ball. Okay. The unfortunate thing about PET is that you buy the scanner and it looks like that scanner that we saw in the picture. It just looks like an MRI scanner or any other old scanner. Unfortunately, with PET, you also have to buy this thing, right? And this is like a particle accelerator in order to bombard various nuclei, usually with protons, in order to create the radionuclides that have a nucleus, that is one of these atoms. And so you have the particle accelerator, it makes those atoms, and then you have this really expensive part, which is this radio pharmaceutical chemist person, right? Who knows how to mix all of these radionuclides into organic molecules and things like that, such that you can inject it into the patient. And so this person is operating, with robotic hands here because inside this chamber, it's just lots of radiation going on, right? These things are radioactive. And so you do all that. When you do your chemistry quickly and you make the substance you're going to inject into the patient, if it only has a 1 minute half-life, you hope that the PET scanner is like next door, right? Or down the hall or something. So this has to be on site, this thing. You can't just do this in Sorrento Valley in some cheap place and then ship the stuff up here. You got to have it right there on site. And then getting it to the room, in some places they'll have a vial, gets tucked away with this sort of O2, like with oxygen 15 in it, water. And then they'll put it in a vacuum tube and it go down the hall really fast and pop out the other side, and they stick it in the patient, right? So in oncology, they do a lot of this. It's called FDG, fluorodeoxyglucose, with this 18F. And it's really sensitive to detecting these very small cancer lesions, sort of that have metastasized to different parts of the body. So again, skeletal abnormalities, for whatever reason, sodium fluoride imaging is worked. And then, PET, it has been used. It was used before fMRI to image the brain during cognitive activity to look for flow differences in cognitive activity, right? Turns out basically functional, neurological functional MRI is much cheaper to do, and anybody can do it on their MRI scanner. Alzheimer's disease is detected with this agent here, or this agent, to look at plaques in Alzheimer's. Viability, the fluorodeoxyglucose tells you whether or not the tissue is alive and turning over metabolically. And then ammonia 13 is basically just a tracer that you inject, and then you rapidly image it as it goes through. So how do we, for any of these agents, we need to take a naturally occurring nucleus like nitrogen 14, and we want to come out with carbon 11, right? Which, is radioactive. And so what happens in this machine here is we're going to bombard this nitrogen 14 with protons, okay? And so these things come with high energy and this could be in a gas or something, and this beam comes in, hits a nitrogen 14. Basically, a helium atom is ejected, or an alpha particle. It's not really, it doesn't have electrons or anything. It's just an alpha particle comes off. That leaves behind a carbon 11. And so that's this unstable carbon 11, which then decays and emits the positron. So that's all going on inside this particle accelerator here. So this is what you do with a carbon 11, for example, as I discussed just a minute ago, that you can put it on acetate, it gets taken up by the cell, it gets metabolized to this, and then you can detect it, the washout of that material. It'll build up as the carbon 11 has high concentration, then it'll wash out by natural mechanisms. So myocytes quickly absorb it, goes through the Krebs cycle. This radioactive substance that has been created by the cell in the Krebs cycle, it diffuses out of the cell, okay? And you'll watch it decay away as it goes out of the cell. So you can measure the rate of washout, or you can estimate the rate of oxygen consumption by the amount that gets created through the Krebs cycle. So it assesses myocardial viability, and what that is the tissue alive or not? So let's go back to the clinic and say, why is this important? If we have detected, say on CT or some other, or X-ray angiography, that there is a critical stenosis in a patient's, let's call it the LAD, for example. We know distal to that stenosis, there is probably abnormal myocardium. It's either underperfused and barely hanging on, but it's still alive, right? It could have lost its normal function. It's not contracting, but during stress, for example, the flow goes down such that it drops out. You say that's ischemic tissue. Question: if we go in and open up the LAD and we put a stent in there and we reperfuse that tissue that we know distal to the LAD is probably ischemic, if we reperfuse it, will it recover? Or is that tissue already dead? That's a big question, because you don't want to go in, do this heroic thing, open up the tissue, it gets flooded with oxygenated blood, it's dead tissue. You cause essentially some kind of arrhythmia by doing this whole thing. You put the patient through a whole invasive procedure only to perfuse dead tissue. That tissue isn't coming back, right? And so ideally then, if you know that, you can just put the patient on optimal medical care, evaluate whether you should put a defibrillator in that patient, such that if they do have a heart attack, you'll shock them out of it, right? And knowing whether or not that distal tissue is already dead saves you from doing that intervention, right? To try and resuscitate that tissue. So that's the whole field of myocardial viability imaging. And it is a significant open question on how to do that optimally for patients that are sort of in a critical stage. If the tissue is consuming oxygen and it's consuming it, say, at a 50% of the normal rate, then you'd say, well, let's go in there and let's open up the vessel because we'll recover that tissue. It'll come back to normal, basically. So that's viability imaging. So, this slide is talking about attenuation effects of the patient on the intensity, the number of hits you're going to get on this line of response. So say over the course of a minute, we're imaging this patient, this detector and this detector go off 1,000 times together. So we get 1,000 basic coincident activations. We say, oh, okay, we got 1,000 of these lines of response. Depending on the depth of the event itself, so if I have the event here, it's pretty well an equal time to here, and it's an equal distance through the patient. If, on the other hand, the event is here, it's still on the same line of response, but it gets out of the patient much more easily. So it's going to get out of here much more frequently than it will up here. In fact, if it's way over here, you'd think the probability of this one getting out at all is pretty low. And so we might not see a lot of lines of response for something down here, right? The fascinating part of this problem is that, and I don't know if it's on the problem set or you just do it at home with ChatGPT's help or whatever. No matter where you are on this line, because this is very high probability of getting out, and this is much lower, and this, they're equal, and this, it's much higher getting out, and this is much lower. It doesn't matter what position you're on here. You have the same probability of getting a coincident event. It's independent of position along that line if the stuff is constant on there, right? So, which to me was a little surprising. I thought if I went, yeah, go ahead. Well, the timing, say I'm here and I have an event, my photon will hit this detector sooner than it hits this detector. Most systems, those two numbers are so small, you can't detect the difference. And so they're simultaneous. It doesn't matter for most systems. Some systems, they do try and measure that time difference to get a bit of, they can measure it with enough precision to get you within like 1/5 of the line or something like that. It's pretty fast, right? Just do the speed of light over like a half a meter. It's like a nanosecond or something. Right? But so the interesting thing here is though, if do I have to do some kind of correction based on the fact that if I'm close, this will have high probability and this will have low probability of getting out. And it turns out you do not have to do that correction. When you actually do the math, regardless of where you are along here, the probability of the two photons getting out and activating the detector is equal. So it's the joint probability of both photons getting out is the important thing, right? And that is independent of depth, which to me was a surprise. But you can look at it. Now, that's not to say that a line of response over here, for example, like this way, might be going through virtually no tissue. So the joint probability of both getting out is much, much higher on a line of response that doesn't have much tissue versus that does. And that's why you need the CT scanner, right? To get that normalization to the whole probability along the line of response. Right? And it says here, for a 20 centimeter path in soft tissue, so like water, the chance of both annihilation photons is about 15% that they both get out. So it's the joint probability of them both getting out. Right? So that gives you an idea of like what efficiency you're dealing with here. So there's a lot of absorption of energy in the tissue. So here's a comparison, given the fact we did SPECT just recently. The big difference is this has the septa and the collimation above the detector, so it makes it far less efficient, right? Because we're only doing one angle, and we have also this very aggressive anti-scatter grid. Because we can do annihilation coincidence, we get much higher detection. Both imaging methods now, previous to deep learning and deep learning taking over medical image reconstruction, in both cases, the reconstruction eventually moved towards an iterative reconstruction technique. It wasn't just a simple back projection technique. It was a technique that had a forward model for how the photons would get out. And then you estimate the image, you create a signal using a forward model, and you look at the difference between the raw data you have and the raw data you created with your forward model. And say, how are those different? And then you encode that difference and go back and change your image and do another forward model and see if you got closer. Okay, and you just do that iteratively until your forward model gives you data that looks like the best fit for the raw data you've got. So if the raw data is noisy like this, your forward model might project into the raw data space, and you say, well, if this is my object, this is the raw data I would have. And when you project in there, you see it goes smoothly through the raw data that has this noise on it, right? And so the image you get is a filtered estimate of what's there, but it's filtered by the probability of being the correct data, right? So those iterative techniques are done both in SPECT and in PET. In order to do those in a reasonable time, you had to buy an expensive computer. And the vendor would sell you a computer that sat beside the scanner, and those computers were often $100,000, $200,000, depending on how fast you wanted to do this process, right? So as you can imagine, vendors jumped all over deep learning because they can do these iterative models on essentially example data, millions of images, and train deep learning to just do it from the raw data, right? Just get this raw data and this image from that. And so that's been done. And so now the cost of reconstruction is like plummeting, right? So you can do quick reconstructions and on small computers just using networks that have been built. They've been at it for 5 or 6 years full time, everybody's come out with their own deep learning reconstruction. Some of them say it's deep learning reconstruction, but all it really is they do a standard, convolution back projection algorithm and then denoise with deep learning, which is an approach, right? So you just say, look, if I make that picture and then denoise to the solution I would get with the inverse thing, then why don't we just learn how to do that? And so that's a number of them, that's what happens really. If they do an underlying standard recon plus a denoising step with their deep learning thing. So spatial resolution in SPECT, as we saw, about 10 millimeters full width half max. And, depends on your collimation, how many angles you take. And this is about 4 millimeters full width half max. Attenuation is less severe with SPECT. And here you really have to use, there's no way you can do it without this CT scan telling you for each line of response what is the expected reduction in sensitivity. So it's really important. Now, here's another important thing. SPECT, when this book was published, which was about 10 years ago, there was like 9 million SPECTs a year done in the US, something like that. It's probably got up to 20 at one point. And PET, there's like 200,000, right? So it's a huge difference in uptake of this technology, right? And one of the reasons is these things are expensive. They require staff that's expensive, and they require professional physicians who are expensive, who know how to use them. They're mostly in oncology departments. And so radiology sometimes has a PET scanner. Oftentimes they'll have a PET scanner. Often when you go to a place like UCSD, all the PET scanners are in oncology. That's the way it is here. So if you want to get a PET, you have to have friends in oncology. And you have to say, hey, on Thursdays, we'd like to do cardiac PET. Is that possible? And get in there that way. And so it really isn't a frontline cardiac technique, even though it's much better than SPECT, right? So here's an example. Here's the CT that's done at the front end of the PET scanner. So it's a non-contrast CT. As we see, there's no difference between the blood and the myocardium because we haven't injected a contrast agent. We just want to know, if I draw a line of response like this, what is the total number of stuff that I have to get through, right? Or a line of response like this. Say I have an event right here. Say there's something here that I'm looking at. This line of response, there isn't going to be a lot of attenuation, right? Because it's flying through the lungs. So that's going to have a higher hit rate than, the one that goes this way through all that stuff. So that's how you have to normalize that. Here's the raw, I don't know if I do it doesn't look like I'm looking at the projection method. We'll talk about that in a minute. So this is a PET image from convolution or 3D filtered back projection, okay? And what that means is we take all of our list data. So let's get a diagram of this thing again. Where is it? Let's use this one. Here's our scanner. Here's our patient. And we're just creating a huge list of number of hits, say of this and this, this and this, this and this, So what we can do is arrange that list such that if we collect all of the events that look like they came from parallel lines of responses in this direction, they come in random order, but I can spatially sort them so that my line of response here, 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 and here, all the way across is going to go in what I will call projection 1, or the projection that's at this angle. So I create a projection just by pooling all of that data together. And if I get multiple hits on this line of response, right, then the signal at that point in the projection just goes up. Like it's proportional to the number of hits I get on that line of response, okay? And then I have to correct for what is in the patient in terms of probability of getting out of the patient at that point. And then I have a profile that is proportional to all of the activity along this line, right? And so this takes us back to the CT world of what I have as a projection through the patient along a line that tells me all the activity along that line. So at that point, we can just do what we did with SPECT, right? Just do this convolution back projection once I've created all of my projections. And so that's what we'll do. Easy enough. And when we do that, it looks like this, right? So when you look at the myocardium, which is what we're really interested in this patient. So this stuff did get absorbed by the myocardium. What is it? It's nitrogen. So it's this nitrogen 13 is attached to three hydrogens, so it's ammonia. And so the ammonia is just a freely diffusible tracer that goes into the body. And so this is the amount of stuff that flowed into the myocardium, right, is the brightness here. And so the question you ask yourself is, so I have a really bright dot here, and then I have a low signal here, and I have, another bright dot over here, then a low signal here. Is that real? Right? Is that difference in signal intensity real? And if you did this in every normal myocardium and it looked like this, you'd say, no, that's not real. This is image artifact. And the reason it's an artifact is because we've essentially up-weighted the high resolution noise on this data. And it's caused this mottly appearance of the image because our filter, which recall we had this filter that started at the origin at 0 and went up like a ramp. It's called the ramp filter in order to do this reconstruction. So we got all this noise. So instead of doing that, you start with this picture, and then we say, okay, I have this picture. If this was my object and I use my forward model to create a new raw data set with this picture. So I create a new raw data set and I look at my actual raw data set and say, what's the difference, right? So the model has come in and basically smoothed it. So then you adjust, given the difference between the raw data and your data, you decide, how do I have to change the picture to get my version of the raw data closer to this one, right? And so it's like a fitting procedure. It's like, I don't know if you've ever done iterative methods for just fitting a polynomial or a line or something like that. They just get closer and closer and closer, right? And then once you've done that, you can essentially fit through noisy data that has this high frequency scatter on it. And you get a blurrier picture, no question, right? But it's a probability estimate for what is the intensity at each point. It's like the maximum likelihood of that pixel being true given the noise model and given the model for how the scanner works. So here's our model image, and this shows that there really isn't, a huge variation at this frequency. Then you can take this hot model. This tells you what's the flow as a function of position or pixel, and map it on top of the CT so that you have context as to where that is in the patient, right? So one thing we can also do is we measure when we inject the agent into the patient, we don't wait around for it to get taken up. We image while the injection is occurring, okay? And we'll put the patient under stress. So this is just like nuclear medicine. We'll image them under stress. with whatever stress agent we have chosen. Remember, we had all pharmaceutical agents, we had exercise, however you want to do it. And so, and then we get an image of the uptake of the agent during that stress. And it looks like at the apex of the heart towards the septum, there is an area where the uptake is considerably lower than the rest of the myocardium. Also at the apex down here, there seems to be something that's critically low. When we let the patient recover and rest and we image again, we see that those flow deficits resolve. So this is just exactly the same way we saw in the ideal SPECT stress test. We see in this case positive flow reduction during stress, resolution of flow during rest. So it's not a fixed defect, it's one that comes back. The big difference between PET and SPECT is on this time scale, these are seconds here. So this is like 3 minutes here. On this time scale, you can see the signal of the left ventricle get, with the agent in the left ventricle, get really bright. I think there's a point missing. I think this second point is probably up here, right? It probably shoots from here up to here and then back down here because this looks like the third point. But that signal is what you would call the input function for estimating the flow that goes to the myocardium. So we get brightness as a function of time with enough temporal resolution that we can actually normalize to the intensity of or the amount of the contrast agent that was injected. It's very important to know this input function in order to solve for the underlying actual absolute estimate of flow per gram per minute, right? We have to know what the input function is. Otherwise, we just get relative values of flow, which we saw in SPECT. And so these black dots here are the myocardium. The myocardium starts off at a baseline count, there's nothing in it. And then as the stuff flows in, our counts, here, the radioactivity in the tissue goes up, hits a peak, and then washes out of the tissue. And this is the agent washing out of the patient's bloodstream, okay? So this slope is an important feature of the curve. If the uptake of the agent into the tissue is very steep, that means the tissue has a high flow rate in terms of milligrams of contrast per gram of tissue per minute. If this slope is a high slope, and if it gets to a high peak, we need to normalize it to what the input is, because from patient to patient, their cardiac output is different. So if somebody has a very weak heartbeat, that their ejection fraction is only 25% versus somebody that's 60%, you can imagine that the rate at which the blood itself just comes to the left ventricle and it exits the left ventricle is a lot slower, right? So it takes twice as many beats. Each beat, a much smaller amount of contrast gets moved. So you need that input function in order to convert this function, which is in the tissue, into absolute flow measurements. So here's some other, so this is venous signal, and this is counts. This is kilobecquerel, it's called, which is like just counts per minute per milliliter. And so the injection occurs, and on the arterial side and the venous side, we see the signal go up in counts and then come down very rapidly. And this was oxygen 15 and attached with 2 hydrogens such that it's water with oxygen 15 on board. Notice it decreases very quickly. So by 3 minutes, we're almost back down to baseline. And that's because this stuff has such a short half-life, right? So two things are happening. It's flowing in, flowing out, going to the kidneys, but it's also losing its radioactivity really quickly. Okay. But it gives us, so this gives you a really sharp input function. And then in the tissue, which is in the myocardium, we see it go up to a peak. This is already coming back down, so it can't go up any higher. There's no future supply of contrast agent. And now it's getting washed out of the tissue. So this whole thing is done in a few minutes, which is terrific, right? Because if you're stressing a person, you do this test, you only need, 5-10 minutes or whatever, and then you can do another one at rest. And so the whole thing's done in a reasonable time. Okay. Anything else about this? So what's the ideal input function, right? For one of these curves, if we want to evaluate this curve at different parts of the myocardium, the input function to the myocardium, if it went along, there's no contrast, and then boom, it went to a very large value of contrast, and then came right back down to 0. Then this entire width of this would be due to behavior in the myocardium. It would not be due to a slow input function, right? So it was like, what is the response of my system? If I put a delta function in, I get what the system is actually doing to the signal. Exactly the same thing this is in time, but we've looked at this in terms of point spread function in space. We put a dot, image the dot, we get a blurry thing. The blurry thing is what the system did to that dot. The equivalent dot in time is bang, a delta function that has huge contrast, then goes away, and we see what does the system do to that signal. Obviously, if it was up for one time frame and then back down to 0, this would not get very high. It wouldn't get this high, but it would come up at whatever the native absorption rate of that thing is, and then it would decay away it wouldn't be governed at all by this, right? If we go back to this curve, you look, this is 3 minutes here. It's down at 4. I don't know how. 3 minutes. That's about the same, right? The 110-minute half-life one, although it's not great for perfusion, right? Because it's going to have a really long tail. So let's look at myocardial perfusion out of a PET scanner using water with oxygen 15. And then this is a patient who is given adenosine, which, remember, is a drug that dilates your vessels. It dilates your vessels in your heart. So you get a higher demand for blood flow. And then when you look at the relative peak signal for each segment of the heart, remember, this is called a bullseye view. This is the apex of the heart in the middle. This is the base of the heart. So it's like a bullet that we're looking at the tip of the bullet, and we can still see the edges off to the side, right? These are higher, they're back away from us. And so we go from the tip or apex of the heart down to the base, and then this is the anterior wall. Remember, the patient's chest is up here. The posterior wall of the heart, the patient's spine would be down here. This is the septum. RV is over here, right? The right ventricle is over here. I don't know why that's failing over there. That's the septum. And then this is the lateral wall or the free wall of the heart where the LAD goes. And the patient's left arm would be over here. So that's the orientation. Done that before. Got to remember it though. You don't want to flip this when you're writing your software, right? It screws everything up. So, and we see there's a lot of flow here, less flow here. It's 100%. We're going to normalize basically to segment 12 by the looks of it. And that's 100% flow. And then this is down to close to 0, right? So this looks like, a significant flow deficit, say in this chunk of tissue here. And this is what you would see in a SPECT scanner as well. You would see bright on this side, dim on this side. Now we take the input function from the left ventricle of the O215, which is this, right? And we use that and this function to determine what is the actual flow in absolute units to the myocardium at each place. And this, for this patient, is the map that comes out of this. You can see there's some of the features are here, obviously. But the really important thing about this patient is what? If we look at these flow levels here, right? Red would be 3.5 milligrams per gram per meter. So that's like a 50% stress or maybe 80% stress. Blue is 1 mil per gram per minute. And this patient is under stress. Normal heart, you go up to 5 milligrams per minute under stress, right? And so when you look at this, you say, well, there's not only a huge gradient in relative flow here, that gradient is way down at low flow levels. And so this gives you a lot more information. You're just like, you know what? This patient, this looks like their LAD might be normal because you've got this whole side of the heart looks like it's getting a lot of flow compared to this side. But you go over here and get the absolute number, you're like, nope, that's not normal at all. That patient has probably triple vessel disease. That means they've got a big stenosis in their right coronary artery, probably a big stenosis in their LAD and in their circ. So when you do the angiogram and you look at this, you expect to see lesions everywhere, right? So this, a lot of people in SPECT, sometimes it'll be 1 and there's no gradient, right? And so for the SPECT scan, it looks like there's no flow abnormality. In this case, at least you could see there was some kind of abnormality. So this is an example of this 18-fluorine fluorodeoxyglucose in tissue that is inflamed, vascular tissue that's inflamed. And so this is a CT scan of a patient's carotid artery. And your carotid arteries are these very large vessels that run up each side of your neck. And so when you're taking your pulse, usually when you squeeze on the side of your neck, you feel the pulse in your carotid artery, these guys here. They're right on the surface, so they're fantastic to image with ultrasound. You can see fantastic pictures. MR, you can put a coil right here and see great pictures. So it's a really nice vessel that way. Secondly, if you need to do surgery, you can just like open it up and just like take it out, put it in some kind of thing. So here there's looks like some kind of calcification, and there's a slight stenosis, although I'm not an expert at reading these things at all. You do know you have 1 on each side, right? You've got 1 over here and 1 over here. This points to, I think, a piece of calcium beside the vessel. But this is the interesting picture. This has high FDG activity in the vessel itself, right? And as you can see over here, we have high FDG activity in this vessel and not on the vessel on this side. So one of the great things about human beings for radiologists is we're very symmetric, right? So you have your own control. So when you're looking at a brain picture, usually there's a left and a right side, right? And in the brain, they're perfectly kind of mirror images. So it's like, well, that shouldn't be there because it's not over there. So it's like an easy way to read radiology. In fact, a lot of times, you can seem really smart when you're with residents and stuff. You're like, yeah, what's that? Why is that there? Oh, nice catch. It's like, yeah, because it's not over there. Here, we've got it over here. It's not over here. And it's a lot of FDG activity. And when basically this thing's a clogged up vessel. And so they'll actually put a conduit in there, or if the person dies, they take that vessel out and look at it. And there was this lesion here, which was highly inflamed. So a lot of um, B cells and T cells and the whole macrophage, invasion of that lesion was ongoing, and it lit up with this. And so if you could do this down on the scale of a coronary, it probably would be useful, right? To say like how you have lesions, they're not, the stenosis isn't critical flow-wise, but my goodness, they are hot, right? In terms of the macrophage invasion and metabolic turnover. And literally they get hot. Just the way when you have some kind of cut on your finger, it gets infected, when you feel the temperature of the infection, it's hot, right? So it's turning over metabolically and creating heat, right? And so that's happening also in your vessels. Some people have actually tried to measure the temperature in there to look at it. So it would be cool to do this in pet. If somebody wants to look into it, I don't know what the progress is of coronary inflammation in pet right now. I knew what it was 10 years ago, but I don't really know what it is right now. So, but it would be a cool project. So this is what that 18F FTG looks like. So it's, as if you remember from organic chemistry, if you took that as an undergrad, or in high school, you took a little bit of organic chemistry, there should be a hydroxy group there, and they just replace it with this. And so it just looks like a sugar, right? And this is a patient's liver who had a primary cancer in their brain, and then this PET agent was injected to see if there's, high activity anywhere in the body. And as you can see in their liver, there's a ton of activity, right? So there's something abnormal going on there. And so this is what the primary use, I think, of PET is in cancer patients. Go ahead. Yeah. So the way cancer kills you most of the time is the primary tumor itself isn't the reason you die, right? So normally you can debulk that, you can treat it with an injection, you can put very focused radiation on that ball of tissue, and you can really shrink that tumor down a lot. However, inside that tumor are different colonies of cells that have modified genetic profiles. And there's like super rapid evolution going on. Who can survive? And so the cells will modify given the bombardment of various therapies to evade the therapy, right? And one of the worst things that can happen is they modify their genetic profile such that they become very metastatic. So they just break off and float away and cause a tumor somewhere else. And that's usually what kills you, right? It's like you just build up this stuff everywhere. And it's absolutely terrible way to die. Heart disease, much better way to die, right? You just fall down, like without even saying goodbye, just like boom, you know. So here, this is an example of basically focal mismatch pattern in perfusion and metabolism, right? So here's the perfusion, and we can see here the metabolism seems to be up regulated or very high in this area. So there's some kind of, metabolic mismatch here between this, just how much stuff is flowing in versus how much stuff is metabolically being taken up, okay? And so they look at these imbalances to decide whether or not tissue is viable or not.